Martin van Duin, after his PhD studying organic chemistry at Delft, he's worked in an industrial R&D innovation environment, performed scientific and technical studies in polymer, rubber, chemistry, technology, both in companies and collaboration with academia. He's author of 180 scientific and technical publications and inventor of 10 patents. While closing my professional scientific career, closing his professional scientific career, it felt like a final intellectual challenge to contribute in some academic way to the field of big history. With a natural science background, I have a strong preference for, he has a strong preference for quantitative approaches, such as Eric Chason's energy rate density as a metric for complexity. Martin?
Yeah, just to make sure you can see the first slide and everybody can hear me.
Yes, very good.
Okay. Yeah, I guess this is a little bit like Monty Python, the English sketches. This is like something completely different again, because I've heard so many different presentations over the last days, and many of them are quite different. And I have to admit, mine is quite different also. The title of the presentation is a critical assessment of the event time interval approach, both for big history and also for big future. And the agenda is pretty straightforward. I will give a brief introduction of the topic. I will give a review of literature using this approach. Then I will spend some time on criticism on this approach. I will try to apply it for big future, and I will end up with some conclusions and recommendations. Okay, now I guess everybody familiar in the field, a lot of big history is about acceleration. That acceleration is not just what people experience or seem to experience in our daily life. It's not only something which we see in technological innovation, like Moore's law, with the number of transistors on a chip multiplying over time. In our human society, there is the term great acceleration, where again, emphasis is on, let's say, these hockey stick kind of plots where certain characteristics seem to explode or show strong exponential growth over time. And in a way, you could say that one of the main trends, at least that's the way I see it in big history, is that complexity seems to increase over time at actually an accelerating rate. Now, of course, we all know that once you talk about complexity and complex system, there's a problem of definitions and the lack of metrics. And I guess for that reason, quite some authors in the big history field have used the event time interval approach, which is a rather simple and practical approach. And in a way, it seems to give very impressive results, as I will show later on in the literature review. So, for those of you who are not really familiar with the approach, I will give a brief explanation. It starts with a list of major events and their timing. Then once you know the time, you can calculate the time difference between the events. And then you can make a plot. Well, you can make a linear plot of the time interval between events and the event number. But then you get these, like I said, kind of hockey stick plots, which are not that interesting, besides the fact that they show that the time interval typically decrease when you approach today. So things are getting faster. Well, typically the data are transferred to a semi-logarithmic plot, and then, well, quite surprisingly, very often rather linear correlations are obtained. And these linear correlations, they are then modeled using different kind of equations like exponential or logistic or hyperbolic functions. And it's actually quite surprising that the R square, which is a measure of the goodness of the fit, is typically approaching like unity. It's 0.99, 0.98, that kind of R-square values. And then a next step in these kind of studies would be the interpretation of the results, and many of these studies have been performed in the context of singularity. Now, the first studies the first people using this approach were Coran and Notale at the end of the previous century. So, for instance, Coran has published a first plot showing the 13 critical transitions from the Big Bang until the human society of today. And he also derived some equations showing that the logarithm of time actually should be linear or expected to be linear with the event number, but what is also indeed observed. Then another paper, well, more or less at the same time, by Notale, again another set of events, but again the same linear plot on a semi-logarithmic scale, and he developed a fractal model, again showing that the logarithm of the time interval should be linear versus the event number. Then I guess work that most of you are more familiar with, that is the work of Theodore Modis. He actually started with a list of 302 events, and he binned them into what he called 28 canonical milestones. And then he again made this semi-logarithmic plot, and again it was linear. He made an interesting point when he prepared his studies, when he said, well, we have this problem of defining complexity, but he said, well, the importance of an event corresponds to the product of the event time interval and the change in complexity. And next, Modis assumed that the importance of these events is comparable. So he said, instead of struggling with complexity, we simply can take delta time, and because that's in a way reciprocal of the change in complexity. Well, he prefers a logistic model, which, in his opinion, shows that the largest complexity change actually has occurred around 1990. He does not support the notion of a singularity. He says that actually developments will start to decelerate. And in a later paper, 20 years later, he actually said, well, there is still no evidence for milestone number 29. Then maybe the last examples of these kind of studies, and the first one you are very surely familiar with, that is the book of Ray Kurzweil, The Singularity is Near. What is maybe not very well known is that in the first chapter of Kurzweil's book, he copy-paste data of Theodore Modis. He does a nice acknowledgement and reference to this, but I don't think it's very well known that this fancy plot, well, this is not from the book, but from the website, that actually these are the data of Modis. It's actually quite interesting to see that Modis says there is a deceleration and no singularity, whereas Kurzweil, using the same data, says there will be a singularity. Okay, but that is maybe not that is not for me to decide on there. Okay, so these are some examples of these kind of studies using time interval, and in the context of big history, there are about 50, well, maybe more than 50 studies, and in a chapter edited in a book edited by Dave and Andrei Korotoyev. There is a good literature overview of all these 50 studies. The conclusion at the moment is that, well, this event time interval approach seems to be a very simple approach, and it has very impressive results. However, there has also been opinion, a lot of criticism against using this method. And I would like to summarize that criticism. And maybe the most important criticism is that the selection of these major events is highly subjective. So this has been mentioned by many people, and I give here some references. And the point is, there is no shared objective definition of what a major event is. And also, there is no quantitative criterion for selection of such an event. So this has resulted in a very renowned historian, Snooks, to state that without such a theory, we are left with a ragbag of evolution in innovation outcomes. Or very recently, there is I have here a quote by Hogarth, and that is that there's quite some criticism of cherry picking, like selecting events in such a way that you get a linear correlation and a semi-logarithmic plot. So the first criticism is about subjective selection. Now, the next criticism is that if you look to the assumption of Theodore Modus, that is that events have equal or comparable importance. I feel that in a way that is shifting the problem of the definition of a complex system to shifting to the definition of importance. So we know that the question, what is more important, a star or a brain? What is more complex, sorry, a star or a brain? Yeah, it's very hard to answer. But I think if you now shift the definition to importance, then you have another question, and that is, what is more important, the origination of a star or the origination of brains? So I don't think all these events have equal importance. Anyway, the importance of the origination of life or the origination of a star or the origination of computers, I would say it's very hard to make a sound statement on that. Then two other points of criticism. One is that all these time data, they have a bias looking at the past from today. And some people have argued, like Kelly and Schmidt-Huber, that is, if you select events from the point of view of today, then typically there's a bias which inherently results in these linear plots in a semi-logarithmic scale. And something similar, that is, if you look to events in the distant past, they get more fuzzy. So in a way, it's almost logical that if you look further back in time, the steps in time will become bigger to see important events. And, and this problem has been called the proximity of the familiar by Myers, or the principle of proportionality by Searle, or the Widdowson has referred to the Weber-Fechner law. It's all, in a way, pointing back to the same thing, and that is, the further back we look, the blurrier the distinctions get. So I think this is more or less a summary of the main criticism against the use of the method. And yeah, when I think about these about these issues, I really have concerns with the method, and I think also big historians should take these issues at heart. Maybe, by the way, these issues which I summarized here also explain why you have R-squared values which are close to 1.0. I would say in natural science studies, when you have an R-square of close to 0, then typically there is a lot of alarm bells ringing, because then typically when you have errors and random effects, then an R-square value of close to unity, that is highly unlikely. Now, what I've next done, and I will show you some results, is that I've used this event time interval approach, but not now looking at big history, but looking at big future. And for that, I've used data from the study by Adams and Laughlin, which, by the way, was earlier today also mentioned by one of the other speakers. So they have published a study, well, more than 20 years ago, which is entitled A Dying Universe. And what they've done, and that was very useful for the purpose of my study, they have looked into the future. Actually, they have looked into the very distant future because they are going as far as 10 to the power 200 years from now. So that is, well, I mean, that is really big future. And they look at the continuation of the formation of cosmological objects, but in this very distant future, these objects disappear, and in a way also matter disappears. Well, the nice thing of having these data from one study is that in a way you have a consistent data set. Also, the way the data are obtained is by doing first principle calculations. So that makes these data sets, yeah, it's one source, it's the same approach. And by the way, it's also only one realm. It's all about the cosmological realm, about the evolution of complexity and also the disappearance of complexity in the cosmos. Now, when you use this data set and you make the typical semi-logarithmic plot, then this is what you get. And when I look at this curve, I think you can distinguish three stages. So first, there is this S-shaped initial stage, which is actually let's say which is actually in a way the big history of cosmology, because today, so the current epoch, that is indicated by this yellow arrow. So this is about the formation of matter and the formation of stars and etc. etc.
We
Then
are getting close to about 20 minutes,
Yep.
approaching it.
Yeah, I will do. So the next step is then this more linear part, where there is still a change in the event time, but it is rather flat. And finally, with this upswing, going into the disappearance of black holes and the disappearance of matter. Now, if you look to these three stages, you could say, well, there are two transitions. One is the transition from a universe which is almost like homogeneous to a universe which contains cosmological objects. So it's becoming highly heterogeneous. And then the second transition at the end, that is this heterogeneous universe going back to a sort of homogeneous universe again, with cosmological objects and matter disappearing. However, you could also look at these two transitions or these three stages in a different way, and that is again by considering the bias from looking at both the distant past, but also the distant future from today. Because if you look at the past from today, you see that the time steps are getting bigger. And if you look from today to the future, you also see that the time steps are getting bigger. So you could also argue that these data, these plots, in a way support the criticism of the time bias of looking at data in fuzzy past and fuzzy future from today. So my conclusion is there is no real way to decide whether these data really show true changes and true deceleration, or whether this is a psychological effect in the way humans look at future or look at the past. So this brings me to the conclusions, and that is that yeah, I do agree that this event time approach is a very attractive approach because it's simple and it gives apparently very impressive results. However, there are quite some issues. And when I try to use these big future data to see whether I could make some more sense about these issues, actually my conclusion is that in the end, especially the time bias, that you cannot really make a statement on that. So I think people who are using this method that they really should take these issues at heart. And Dave, a few days ago, there was a small side discussion, and you mentioned that, yeah, there is a problem in big history is that there is a lack of good metrics, which I agree. But let's say the fact that we lack good metrics to follow the development of complexity over time does not mean that we should metrics where there might be some deficiencies. So, considering these issues, I have a very strong preference for the use of objective and quantifiable characteristics. And that, well, I copied this slide from Paul from his presentation a few days ago, because when he talks about good science, he also emphasizes objectivity, and he also emphasizes that you should not do rationalization. You should not be selecting evidence to justify your conclusion. And I would say, well, in the area of big history and all these subdisciplines, actually there is a plenitude of alternatives. There are so many objective and quantitative characteristics, and this is a non-comprehensive overview, and I will not going to read all of them. But many of these characteristics, they are about the magnitude of a particular characteristic, the size, the mass, the energy rate, the number of people. I mean, these are all quantitative data, and you can use them in big history studies. And another kind of quantitative characteristic is more related about diversity, which is about the number of types, the number of types of languages, the number of types of molecules. So, okay, maybe in the last in my last sentence. So, I really prefer to use these kind of approaches with these kind of data, and I think we should move a little bit away from this event time approaches, because I'm not really sure whether they have a real big added value for big history. Thanks.
Excellent, Martin.
I have to acknowledge two people, so Esther Kwaatakkers and Georgie Georgiev, who are I have regular discussion with them, and they are coaching me away in my studies. And thank you for your attention.
Thank you very much, Martin. That very nice, and it really brings in to perspective. What are we trying to do, and what is the data that we're kind of leaning on, and what is the validity of that data. And I think you've done excellent work on the energy flow, and I really appreciate that. And Martin has a number of papers in the journal Big History with more details. Ken, go ahead.
Oh yeah, thank you, Martin. You bring up some really important parts. For those of you who don't know, I'm an retired ER physician, and had long drives to work, and I would listen to 40 studies in medical literature a month. And fortunately, the discussion was with a very intelligent guy on methodology, and a doctor, I should say, and I know him personally. And in medical literature is also a problem with the very things that you're pointing out, that you have to define what you're looking at ahead of time, and make sure you're not cherry picking data. Medical issue, and right now, forget the CDC United States, because they don't know one type of study from another. So sometimes you can pose a question and put multiple parameters out there.
Ho sbagliato tutto.
But that's the hypothesis generating stage. And then you have to go to the next. If something pokes up, like, every time this happens, we got an increase in complexity. When you've looked at 10 parameters, you got to then go back and look to see if that holds up with a different analysis. Because just by chance, if you pick enough different things, by chance, one of these will fit a line or something. So, I've worried about that, and I know I've talked to Dave Lepore as well about concerns about cherry picking data. You got to define what you mean ahead of time, which is really difficult in complexity because it causes so many regimes and so forth. So thank you for bringing that to the fore. I wrote a paper that critiqued Chazon's free energy rate density because there's some real methodological and even a logical flaw in his analysis. And I won't get into it, but the most critical one was using your own metric as its own gold standard. You can't do that until you prove your gold standard is a gold standard by comparing it to other metrics. So thank you for bringing a lot of these issues to the fore, Martin.
Yeah, okay. Okay, and thanks for your comments. And also, by the way, it's good to see you almost like real life again, because we sometimes have this email exchange, and now it's good to see each other.
Allora, adesso chiudiamo,
Gerard?
Yeah, hi Martin.
Hi.
We have also communicated via email.
Yeah.
And I actually appreciate the outcome of your research in the sense that it says that you cannot make a ranking from things that are not of the same type, which is another way of saying that you aggregate data from different systems and put them in one line. I have made a line like this for the operator hierarchy, because there you are certain that you only work with systems of the same type. All the systems have dual closure and follow each other sequentially in a hierarchy. So I think that allows you to put them in a ranking. It shows exponential increase of complexity, but it's not sort of a very direct R square type of hierarchy, but you can see that it works. And at least then I'm sure that I work with the same type of systems.
Yeah.
So, yeah, I think that would be an advantage of this method, and that would take into account the what do you say, the warnings that actually come from your work.
Yeah, I agree with you that if you, I fully agree with you that if you take data which are based on the same argument, then you have a consistent data set, and then I think it's fully okay to apply this method and make those kind of plots. Yeah. By the way, there's maybe there's one thing that comes to my mind now, and that is that so if you look at, let's say, many of the big history studies that are using this method, they all point about acceleration. And some of them even go as far as the occurrence of a singularity. But on a cosmological scale, you could say that complexity goes through a maximum. If you look at the rate of star formation, that has already peaked, like 9 billion years ago. If you look at the rate of black hole formation, that more or less peaked at the same time. If you look at the rate of planet formation, that has peaked like 8 to 9 billion years ago. So if you and then if you look at, let's say, the very distant future, where one of the scenarios is that the universe will go to a heat death or a big chill or whatever kind of word you would like to give it, then it's clear that let's say this acceleration for local complexity on Earth, that at some point in time it will change over to deceleration, which is happening in the universe all over time.
Andre?
Yeah. Oh, I already demuted myself. Thank you for the talk. I was fascinated by how you're developing a kind of mathematic model of evolutionary history. And again, it's a kind of system theory, which I very much appreciate. In my talk, I think I left the impression that I was dismissing systems theory. And I think systems theory is fascinating and enriching, and it can lead to all kinds of recognitions of the connections of things. But the more specific point I wanted to make was what I also find is your dilemma is that you have the kind of structural logic of a mathematic approach that you're trying to uh, use to interpret phenomenal events. And it's the old struggle between logic and rhetoric, or structure and phenomenon. And I find that struggle fascinating and leading to all kinds of interesting insights. And I'm wondering, how you negotiate that struggle. I mean, you did it very well when you listed your own criticisms of the structural approach coming from the phenomenal perspective of how do you quantify events? How do you identify events? How do you weigh and value events? I think that's the phenomenal nature of history that you're struggling with to interpret in a mathematical model.
Yeah, but okay, so but let's say drawing this kind of conclusion myself, if I look to the kind of studies that I still plan to do, then I'm going away from, let's say, this kind of approach and try to use other really quantitative and objective data because, well, maybe it's also because I have a beta background in natural sciences. So I'm a chemist by education, and I've worked in polymer and rubber chemistry for 35 years. So for me, if you don't start to use quantitative and objective data in your studies, you in the end you end up with models and almost like opinions and never-ending discussions. I think quantitative data, that's one of the few ways to decide what is correct and what is wrong. And you have to, that is what you have to do. You have to do the falsification and the validation. Otherwise, you will never make progress.
Yeah.
I'm gonna just let people know it's 11:05 about. So if you want to take a break before the next speaker, Dave, you can take over, whatever you like.
Yeah, just had one comment, and then we're actually going to take a break after that. The break's a little bit earlier today. But, I think quantitative analysis is great, but I think you have to work with what you have. And I think I pointed this out, or had discussion on this with Martin. Like in physics, the fine structure constant is one of the best known agreement between theory and experiment out there, right? It's 9 or 10 significant digits long in agreement, and even a small difference at the very end can shake up physics. And they're trying the same thing with muons, and that's been getting a lot of attention. But in the other area that I work, kind of in the response of humans to low levels of radiation, ionizing radiation, we really don't know. We don't even know really the sign. Is it beneficial or harmful? And so, in a scientific point of view, that's very tough, but something has to be done, right, in terms of regulations. And so, like you said, Martin, they make models, they extrapolate orders and orders of magnitude from whatever they have. And this is a real big issue right now. People are pushing for less regulation of things, and they're saying like, there's no scientific evidence that this harm actually occurs. There might be benefits. Why are we doing this? Why are we spending all this money? And it really relates to big history in this particular way, is that low levels of radiation impact cells, and cells have been around, have evolved for a long time, billions of years. And in fact, in earlier evolution, the radiation levels were actually higher. than what they are now. And so it really is a question what's happening at the cellular level. And people are trying that, but it's a very difficult subject because they have to go from single cellular then to multicellular levels. And I think in big history, it's even kind of a more complex system. And we need to be kind of cognizant, as Martin pointed out, of some of the difficulties. But even if there was a tape, a recorder of every single event that ever happened, I think it would still be difficult to come up with exactly quantitative measures of what actually went on. And I think this discussion could go on and on, but I think it's very important. But I think we'll be continuing this discussion for years. And I really appreciate what Martin has done in this.
Okay, thanks.